The objective of this video is to summarize the operation and compare the device requirements of the buck, boost, and buck-boost converters. I want to start by doing a review exercise. I want you to sketch in your notes what the buck, boost, and buck-boost converters look like below each of the headings. Use the full converter with a semiconductor realization. Hit pause, and when you're ready to resume, press play. Your notes should look like the following. If any of this is surprising to you, I suggest that you go back and review the previous video lectures and assigned reading for the buck, boost, and buck-boost converter. We're now going to summarize various results that we derived in the preceding 3 videos for each converter. We're going to do this to compare the converter requirements and extract some fundamental nuggets of information that help us decide which converter is necessary for our application. When picking between the buck and the buck-boost converter, this exercise may seem trivial. We can note the voltage out over voltage in expression for the buck converter as being a function of D, where in all cases D is the duty ratio of our MOSFET. And for the boost converter, V out over V in is equal to 1 over 1 minus D. So if you're trying to pick which converter to use, you simply have to decide based on what your output voltage requirement is. If it's less than your input voltage requirement, then you want the buck converter. If it's greater than the input voltage requirement, you want the boost converter. But the plot thickens when we consider the buck boost converter because it's able to output a voltage that's both greater than or less than our input voltage. So at a first pass, you might decide that you would always use a buck-boost converter. However, the next several lines that we're going to add here are going to show you why this may be a bad idea. If we compare our average inductor current for each converter, we see that for the buck converter, the average inductor current is equal to I out. For the boost converter, our average inductor current is equal to the input current. But for the buck-boost converter, our average inductor current is equal to the sum of the input and the output current. This means that the buck-boost converter requires you to have the largest inductor, the most expensive inductor. You need the greatest amount of copper in this inductor in order to carry the required current. If you know that your output voltage is always greater than or always less than your input voltage, then you should choose a buck or a boost converter in place of the buck-boost converter. We can also look at this in terms of the device blocking voltage. And by this I mean, what is the voltage that your MOSFET and diode have to block for each converter in terms of the input or output voltage? For the buck converter, clearly the devices have to block V in volts, whatever your input voltage rating is. For the boost converter, it's V out, but for the buck boost converter, it is V in plus V out. This is a result that we derived from our previous lecture, but you can see it from having to sum up your input and output voltages as appearing across your MOSFET or diode. We can similarly size the average MOSFET current and average diode current. For the buck converter, the average MOSFET current is IN. For the boost converter, it is D times IN. And for the buck boost converter, it is equal to IN. The average diode current for the buck converter is going to be 1 minus D times I out. For the boost converter, it's 1 minus D times I in. And for the buck boost converter, it is equal to I out. And we can note that for the boost converter, I in is equal to I out divided by 1 minus D, So simply the average diode current is equal to I out. And you can see from this analysis that the buck boost converter is always requires more current, the same or more current for its devices as the buck or the boost converter. Next, we can sketch what the average input current waveform looks like. For the buck converter, we commented that you have a discontinuous waveform. During interval 1, when the MOSFET's conducting, your input current is non-zero, but during interval 2, when the diode is conducting and the MOSFET's off, the input current is 0. The boost converter stood out in that its inductor current or its input current was a continuous waveform. And then we also remarked for the buck boost converter that the input current is discontinuous, similar to the buck converter. And the reason that this is important is that in some applications where you want to have a smooth current profile, we can see that both the buck and the buck boost converter may require an input filter. So based on this analysis, we can see that the buck boost converter is always inferior to both the buck and the boost converter when looking at any single design metric. However, it has a unique capability of being able to offer you an output voltage that can be greater than or less than your input voltage.